Okay. Since, and I keep putting it down, if I'm looking at the circle and figured out that if my arc length is 1 radian, or 1 radius, the length of whatever the radius is, that angle is 1 radian. If this is 2 radii going around the outside, this would be 2 radians. So we have this relationship that whatever the length is along the arc, that's going to be equal to the radius times the angle in radians. This is a relationship, I sometimes think of it as standing room only, because it kind of looks like SRO, but this is the arc length is equal to the radius times the angle in radians. So, for example, if I have a circle of radius 2 meters, and I cruise around and I have an arc length of 3 meters, what is that angle? Plug and chug. I got 3 meters is equal to 2 meters times theta. If I'm solving for theta, I divide both sides by 2 meters. And don't forget, this theta is in radians. So what do I get? What is 3 meters divided by 2 meters?
2.5.
Not 2.5.
1.5.
Yeah, 1.5. What about the units though?
Meters.
They cancel out.
They cancel out. Now I said the angle would be in radians, except the units cancel out. It turns out that the radian I refer to as a unitless unit. You could put it in or take it out. Inspiring a student a number of years ago to put radians at the end of all of his answers, because why not? Now typically, why would you put radians in if you don't have to? For clarity. If I said an angle was 10, if I were correct, it would have to be assumed 10 radians. But if I said that to somebody that the angle was 10, you might wonder, did he just forget to say degrees? And so you put it in just for clarification purposes, but technically you don't have to. Other questions? I'm now going to drop back to that other screen. There we go. So instead of V here, I'm going to put in omega R. And you might not believe it, but I am about to make this whole thing simpler. So I put in omega R. Now notice I do have a subscript next to R because where I am, R is the distance from my axis of rotation to whatever mass I'm talking about. But I don't have a subscript next to omega because it's a rigid body. Everything is moving at the same angular speed. It will go through the exact same angle in the exact same amount of time. That is equal to 1/2 times the sum of mi omega squared r sub I squared. Because omega is the same for everything, for each term omega squared is the same, I can factor it out just like I did with the 1/2. So that is equal to, so my kinetic energy, 1/2 omega squared times mi r I squared. Now you're looking at it and going, oh yeah, okay, now it all makes sense. I got one more step to go. This MIRI squared. Again, the math people, what they've done is they've taken an object and broken up into a whole bunch of tiny little pieces mathematically, and they figured out the mass of each of those tiny little pieces times the distance squared, added them all up, and you end up with what is known as the moment of inertia, the rotational mass analog. So when I'm doing the kinetic energy of an object that is rotating, That's why we have a formula of 1/2 I omega squared. 1/2 mv squared is at the heart of it, but it's how you deal with an object where not everything travels at the same speed. And while people are writing that down, I'm just gonna let that run. I'm gonna go grab the textbook. All right, so potentially, at this point, you're thinking, great, but how does that help me? What the heck is I? Well, the bad news is, in order to find I for an object, you need calculus. The good news, somebody's already done that for you. Each shape of an object has its own special formula. For example, if I have a hoop rotating about the central axis, so I've got an axis right here, the moment of inertia is just the mass of the hoop times the radius of the hoop squared. If I have a disk rotating about a central axis right there, so like a wheel, a solid wheel spinning, the moment of inertia is 1/2 mr squared. I'll do one more and then I'll talk about how you can do this too. If I have a ball, a solid ball, the moment of inertia, 2/5 mr squared. M is the mass of the entire ball, R is the radius of the entire ball. Now, how can you know this? It's going to be true in pretty much any physics textbook, or at least beginning levels. But page 138, there's a table here that is common to most beginning textbooks, where they give you the shape, give you where the axis of rotation is, and it gives you the formula. So that's where you know it. On a test or quiz, you look on the first page. On a test or on a quiz, you look at the top, and I'd have the formulas there. Questions here? And I'm going to grab 2 more props. And we're going to see if physics by democracy works. what I'm gonna do is I'm gonna set up an incline. Wherever I put it, there we go. And I'm gonna roll stuff off the edge. So the first thing I'm gonna do is I have two objects here that they have the same radius. I can't tell which one is more mass. I think this one is more massive. That has more mass than this one does. If I race them down the track, which one is going to get to the bottom first? Now, whether you know why or not, whether it's just a random guess at this point, I want you to have an opinion and vote. So we have the hoop, we have the solid disc, a tie, and then neither. So which one's going to get to the bottom first? So the hoop, who says this will get to the bottom first? Who says this will get to the bottom first? 1, 2, 3, 4, 5. Is that a vote for it?
No.
5 people. So 0, 5. Who says it's going to be a tie? Looks like 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Neither? And an homage to a comic book I had when I was a kid. All right. Any of you willing to bet your grade? A or F? You trust you?
So we get ready to get
All right. It's more of a question of whether you'd be willing to, not whether I could do allow that, because I've had enough students very confident with the wrong answers before. All right, here we go. I think that one clearly won. See, that was the disc on that side. Now, sometimes there's board bias. This is a better board than I used to use, so that should be less of an issue, but just in case the board is not exactly. Oh. Yeah, because the solid was closer to you before. All right, so physics by democracy did not work. So congratulations to those 5. Why? Give you a chance to speculate. And it's okay if you're wrong. We'll eventually address that. Genesis?
Because the mass is a little bigger, or greater, sorry.
So the bigger the mass, the faster it'll go? Is that?
Sure, yeah, that's what I'm saying.
So if I took these two, which one has a bigger mass? That one has a bigger mass. So you're saying this would get down to the bottom before this one does? That's based upon what you just said, that's what the implication would be. Is that right?
Okay, yeah. I'll just.
Were you saying something different or misunderstood?
No, I don't know, honestly. I'll just stick with that,
Okay,
even if it's wrong. I'm sticking with it.
all right. Way to have conviction. All right, so the speculation that I heard, whether it's what she said or not, was that the more massive one, this was more massive before, so this is more massive than this. So under that speculation, this should win. All right, the more massive one did not win, so it's gotta be some other explanation.
That one's solid. That one's solid. Air, so the air.
I don't think it's going fast enough for air resistance to be of significance.
But it's because that one's solid.
It is solid. So if, other than air resistance, why would solid make a difference?
Other than air?
What was that?
You said other than air?
Yeah, ignoring air resistance. All right, let's see if we can narrow that down. I have two solid discs. Obviously, one is bigger than the other. Which one would you, which one would win, or would it be a tie? Or will they burst into flames all the way down?
The little one?
Think the little one will?
Yeah.
It's solid though. Why, what, did you have a reason why?
Yes or no?
Yes. Nothing, that just gut feeling right now?
I don't know how to explain it.
Well, let's see what the class says. So we got the small one, the large one. We'll take neither off the table. I am gonna hope that they don't burst into flames and disintegrate before they get there. When I had the old board, sometimes they fall off the edge. But... All right. Small one. 1, 2, 3, 4, 5, 6, 7. Large one. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that was 9. A tie? Anyone feeling confident to get a grade on this? Gambling is wrong. But it's the way you can make money in physics, is the side bets. All right, no. I'm glad I'm recording that. All right, here we go. Slightly faster. Try the other side. Pretty darn close to a tie there. Why? I mean, it's clearly, this is twice the radius, and I'm gonna guess probably 4 times the mass. It wasn't a huge difference in what happened.
I didn't see it. Did the small one win?
That last one, it was pretty darn close to a tie.
Okay.
Tell us why, we don't know. Tell us why, tell us why.
Not yet. 2 hoops. All right. Who says big hoop's gonna make it down first? A couple brave souls there. Who says the little hoop? Who's going for a tie? Anyone have an explanation for why they think that? Which way they went?
I'll say because it's bigger.
Bigger one?
Goes, you know, one track, the taller person got longer legs, so they.
The classic. It's like watching the marathon and the commentators making the comment, if it's a tall person, it's the legs are longer, fewer steps. If it's a short person, they say smaller mass, therefore less to move. Small one slightly. Now, some of you said the small one, if you were thinking that it's gonna win, but not by much, congratulations. I would expect this one to win by just a little bit. Radius is about the same. Solid ball versus disc. I guess I should ask the question. Disc. Solid ball. A tie. No one for the tie. Now this one I need to make sure that it's somewhat level here, because balls notoriously can go in any direction. All right. Pretty darn close to a tie. I would expect the ball to win by a little bit. All right, so let's see if we can get into some reason why. Hint, it has something to do with moment of inertia. If we think about it from an energy point of view, it starts out with all this potential energy, that potential energy gets converted into kinetic energy as it rolls down the incline. There's two different motions going on here. There's the spinning of the ball, or the disc, and then there's the linear motion, the fact that it is moving down a ramp. We got two different types. So, if I have all this potential energy, that's going to get converted into kinetic. I've got my linear kinetic, the 1/2 mv squared, and my rotational kinetic, the 1/2 I omega squared. Excuse me. The more energy required to get it to roll, the less energy is left over getting it to move down the ramp. So the more energy that goes into this, there's less energy left over for that. Well, what's going to make a huge difference here is that moment of inertia. If I look at the hoop, the moment of inertia of the hoop was mr squared. The moment of inertia of the solid disk is 1/2 mr squared. What's the big difference between these two formulas?
1/2.
If I went to the solid ball, it was 2/5 mr squared. Based upon the math here, and what you know at this point, which one would you expect to win? I think someone said it, but
The ball.
yeah, the ball, because that's smaller than that is.